a minor but important detail. You recall our talk about the slope of the tangent line, and we had this secant line. So this is the red line. If you can see, this is my red line is the tangent line I've drawn here. Let me make it better in sort of whitish pink here. So this is my tangent line, and I want this secant line to be getting closer. Now what happens is x is getting closer and closer to a. You remember why we needed the secant line in the first place? In order to have the slope, we need to have rise over run, which means we need to have this distance and you need to have this distance. That cannot equal 0. We're not allowed to have the run, this horizontal distance, be 0, which is to say we're not allowed to have x equal a. That is not allowed. Now, what that means is this. The distance between x and a now we know that cannot be negative. There's no way this can be negative. But could this be 0? Well, if x is equal to a, then we have 0. We don't want to have that happen. So this is a requirement. When we write this statement, there's one extra piece of the puzzle. We are not allowed to have x and a equal each other, which means if they did equal, x minus a would be 0. If they were equal, x minus a would equal 0. We do not want that to happen. We do not want that to happen. We do not want 0 to equal x minus a. If x minus a is equal to 0, that means x is equal to a. That is prohibited. Since x is prohibited from equaling a, that means x minus a is prohibiting from equaling 0. And so we account for that with this little minor adjustment. It's right there. 0 is strictly less than x minus a. Now, what about the less than part? Why don't you say x is, well, this can never be negative. We know, if here's the number line, there's 0, and x minus a must be over here somewhere because x minus a must be positive. Not allowed to equal 0, so x minus a is greater than but not equal to 0. All right? So that's why we do not use this. We do not use or equal to because we're not allowed to have x equal a. So when we write this little piece, this is the official mathematics way of saying x is not equal to a. What happens if x does equal a? And the answer to that question in the calculus, anytime you're dealing with limits, anytime you're dealing with limits, world without end, amen. Anytime you're dealing with limits, if the question is, what happens when x is equal to a? The appropriate answer is, I don't care. It does not matter what happens when x is equal to a. For limits, we are not, no matter what anyone tells you, no matter what happens, when we compute a limit, we do not let x equal a. We are not concerned with what happens as x is equal to a. It's going to look like it. We have to remember the logic, and it's going to be something slightly different. It looks like it, but it's not. X is getting very, very close, but not equal to a. X is never, ever equal to a when we're talking about a limit. For our purposes, if the question is, he said, reminding them that a multiple choice question is coming up before too long. If the question is, what happens at x equal a? The appropriate answer is, it does not matter. It is irrelevant what happens at x equals a. It might work, it might not. If it does, fine. If it doesn't, fine. What happens at x equal a is completely irrelevant. The way you write that mathematically is that. So when we write for any epsilon greater than 0, when we wrote that at the end of the previous video, it says if we have, and we had x minus a less than delta, we actually need to include one other small detail. That detail means x is not equal to a. Then what needs to happen? What needs to happen is f of x minus L must be less than epsilon. And it's a technical thing that we'll talk about in a little bit more detail later on. If this is equal to 0, that's fine. It's irrelevant. What happens on the y-axis is irrelevant. What we're looking for is what's happening on the x-axis. So on the y-axis, as long as this is happening, equal to 0, it turns out, is just fine. This is the official definition of a limit. This is the definition of a limit. And that's what we're going to be going with from here. And so let's put all this together into the official statement now. We write the following. L-I-M. This is easily the neatest L-I-M you will ever see me write. You've already seen my, this is penmanship, it's chalkmanship. You've already seen my handwriting. It tends to not be fantastic. But L-I-M, it stands, L-I-M is the first 3 letters of the word limit. I don't know if you picked up on that or not. So it's the first 3 letters of the word limit. And underneath you write X, arrow, A. What this means, you read this as the limit as X approaches A. Or sometimes people will say the limit as X goes to A. Or the limit as X gets close to A. All those words are essentially interchangeable. They convey the same meaning of these symbols. The limit as X approaches A. Limit as X gets close to A. What this means that. The limit of a function is equal to L. The limit as X approaches A of f of X is equal to L. Let me show you what that means. What this means in terms of the symbols. This means, this is the definition. The definition is this. What I'm going to write that, I'm going to write exactly that same thing there. For any epsilon greater than 0. If 0, why is this here? Why is this here? This is here because we do not want X to equal A. This guarantees X is not equal to A. What happens at X equal A? Don't care. What happens at X equal A? We don't care. If this occurs, if you're well behaved on the X axis, then you will be well behaved on the Y axis. This is the fancy schmancy way of saying what's happening in this picture. Here's A, here's L, there's epsilon, there's the function, there's delta. So this is an epsilon interval, there's the delta interval. The limit is a way of saying, another way of saying is, what is it you're getting closer and closer to on the y-axis? For this function, approaching that number, what are you getting, as you get closer and closer to this number on the x, what are you getting closer and closer to on the y? All right? As x gets closer and closer to a, for this function, you're getting closer and closer to L. As I choose x values here, they get close to a, the function values get closer and closer to L. The one way to violate that is if we have a jump. If there's a jump, then this is a violation. Another way, we'll find this out later on, another way to have this foul up is if you have a vertical asymptote. If there's a vertical asymptote, things go wild. But if this is a nice, smooth, well-behaved function, this is what's happening. This is the official way to write out what's happening for a nice, smooth function. And this explains why you didn't bother considering this way back in your basic algebra class the very first time you do the graph of x squared, because this was much too much to consider at that point in time. So let's do a specific case. Let's do a specific case. Suppose f of x is, I'll just pick something out of the blue sky, 2x plus 1. And suppose a is, let's just pick something out of the blue sky, 3. As you get closer and closer and closer to 3 on the x-axis, for this function, as you get closer and closer and closer to 3 on the x-axis, the question is, what are you getting closer and closer and closer to on the y-axis? Well, it turns out, in this case, it's 7. And we'll deal with the details of that later on. But it turns out that as you get closer and closer to 3 on the x-axis, in this case, you're getting closer and closer to 7 on the y-axis. And so in this case, a is 3. In this case, f of x is 2x minus 1. And in this case, 7 is L. So for now, don't worry about the details. Suppose I just give you this. Suppose you're given lim x approaches 2 of x squared minus 4x is equal to negative 4. Suppose you're given that. What you need to be able to do for now is recognize, what is L? For this problem, what is L? L for this problem is negative 4. What is A for this problem? A is 2. What is f of x for this problem? F of x is x squared minus 4x. For now, just be able to recognize and label the pieces. We'll work with how to flesh this out later on. But those are the pieces. Usually, if the value you're approaching is a negative, what I will do is I will put the negative in parenthesis just to emphasize that it's negative, just to keep clear, and that sometimes that negative sign gets dropped in the wash. And so if we have x approaches negative 2, maybe this is equal to some, I don't know, 12 or something. So in this case, a is negative 2, f of x is x squared minus 4x, and L is equal to 12. So for that problem. So for now, just be able to recognize what pieces belong where, and then we'll talk about how to flesh all this out in detail.